Hi, I'm Taylor Grace, and I am a junior and biochemistry major at Stephen F. Austin State University. The title of my poster presentation is The Binding Studies of Plant Flavonoids, Quercetin, and Maurine with Human Serum Albumin, a Temperature-Dependent Study. I would like to first give you a brief introduction about flavonoids. Flavonoids are these polyhydroxy compounds that are found in citrus fruits, red berries, onions, plants of that sorts. And they hold these anti-cancer, anti-AIDS, all of these different medicinal potential values. I have research into maurine and quercetin as they are very similar in the structure. You can just see briefly like this, but there's a slight difference where in maurine there is a 2' 4' dihydroxy group in this B ring, whereas in quercetin in this B ring it's a 3' 4' dihydroxy group. So I wanted to study those two flavonoids and how it would bind to human serum albumin. As human serum albumin, it is a drug transporter, a natural drug transporter inside of our body. And as it binds to the drugs in cellula 1 and 2, as we will look more into that with maurine and quercetin. The following techniques I use absorbance and fluorescence spectroscopy, and hope in the future to use circular dichroism, which is CD, to look more into like the secondary and tertiary structures of the protein. The main biological target that I really wanted to look through was the protein, and which was I am using my HSA, my human serum albumin. My three potential channels of gaining information, as you can tell in this first one, all the way over here to the left, there is the excitation and the fluorescence of the tryptophan. And then you have all the way over here in the middle, you have the excitation and the fluorescence of the ligand. And the ligand in our study is the maurine. And then right for here, you'll see the excitation of the tryptophan, which is only one single tryptophan inside of HSA, and it's an aromatic amino acid. And we have the fluorescence of our ligand. And this will only occur if there is some type of energy transfer, which we'll go into more later in our results. So my main objectives was to study the chaperone activity of maurine and quercetin and protein folding in the following temperatures of 15, 20, 25, 30, and 37 degrees Celsius. In my presentation today, I will only be showing you the 15 and 37 degrees Celsius. Then I wanted to compare the behavior of maurine and quercetin. So before I go on to my results, I wanted to talk about my HSA solution and my flavonoid solution. My HSA solution was made in PBS buffer, pH of 7.43, and I used its molar mass and its molar extension coefficient at 280 nanometers to calculate with Beer's law to find the concentration. And then for my flavonoid, I made it in ethanol because flavonoids are not water soluble, and I only made it up to 30 micromolar because I want to avoid aggregation at higher concentrations. So when we first look into my binding of HSA with maurine at 15 Celsius degrees, you can tell by this absorbance graph, as the red goes to blue, our HSA concentration goes from 0 to 40. So lower concentration to higher concentration. We notice from red to blue, our absorbance increases as well. So overall from this graph, we got as we add more HSA into it, the absorbance will increase as well. From this graph, we got our normal fluorescence of our maurine, our normal emission scan of our maurine, but we notice that there is another peak, which is our tautomere. Our tautomere is when a proton from this hydroxyl group in the C ring right here, this hydroxyl group will be, the protein from here will go to the ketone, as that will be an excited state proton transfer, as this only happens in the excited state at this as it spot right here at 350. Then we we know it's maurine because it's around 460. So then we looked at the excitation scan, and it emits at 530, and we noticed that there's no crazy structural change, as it's around maybe like I don't know, it's a peak right here, maybe around like 380, 390. But we wanted to look more further of where our tautomere, and we didn't notice anything drastic changing over here, which is great. So we know that we knew that it wasn't like any other thing. If it would have been another peak like this, if it was not a tautomere, it would have been another heel. It could have been a different compound, then something else will be going on. So then I wanted to look more into HSA with boron at 37 degrees Celsius, and notice that the absorption, it looks pretty similar to the 15 degrees Celsius. As the concentration increases, so does the absorption. So then we look over here in our fluorescence, we notice there's no tautomere present in here. But then we look over here, it's pretty similar to the one before. So that means all the structural looks pretty similar in boron, as boron is constant at 30 micromolar. And overall, from the point we got from these graphs is that as the flavon is constant at 30 micromolar and our HSA increases, so does our fluorescence. And then in here we got Forster resonant energy transfer, FRET. And this is where we notice that usual around our normal excitation scan of our ligand, which we saw it's at 350, right? So we look around here, we notice a peak similar to near 350 around the range. And then we notice that right here, right around 295, and the 350 that's just a usual flavonoid. It's nothing very like specific usual flavonoid fluorescence. When we notice a 295 right here, that is a peak for tryptophan, which proves our channel of information getting right here. That will only happen, this peak will only happen if the flavon, the morin, is binding to the HSA so near to the point of where that single tryptophan that's only one present in the human serum albumin is near that binding. So the tryptophan, which is presented in the HSA, is going to be near where the binding occurs of the morin to the HSA. And this shows us the proof. So then we wanted to look more into these graphs. We notice that as our temperature increases, so does our intensity. And this is our fluorescence for our tryptophan. So we notice that once the temperature changes, there is a drastic change within the intensity. And then we look for at our tryptophan, which is at 520, we notice from right here in this peak that when the temperature increased, the temperature didn't really change much. It wasn't much of a change, so no drastic change as you can compare it to this from 700 all the way to almost 1200. And then for right here at 460, which is our normal morin fluorescence, we notice there is a drastic change as it goes from 50 to maybe over 80 and as an intensity. So there is a drastic change. We use this equation for our I intensity with protein at whatever concentration, and in our I with no protein, the I for intensity. And we used it for our binding constant. And we noticed that as our temperature increases, which we really prove over here, so does our binding constant using this equation, as 37 degrees Celsius will be at its highest. In conclusion, we notice that there's drastic changes in fluorescence of both tryptophan and morin as observed at different temperatures. As we did say, it goes from 700 to 1200, and it goes around 50 to over 80. Morin influenced the folding of the protein HSA to a significant extent, as we can prove this point because morin does influence it, as there is an energy transfer. Remember the tryptophan peak and the morin peak. And in the future, we hope to compare the morin with quercetin behavior and human serum albumin protein more as we are continuing to go on through that, and then study neural proteins, and like I said before, use circular diachroism to study the secondary structure. Thank you for your time.